Okay, I'm ready to get started. Roughly, it looks like everybody's here. A lot less seats occupied than a few weeks back, but it's fine by me. Whatever works is what I say. Okay, what I'm going to do is say a few words about what not to worry about for the quiz, even though you're probably worried just the same. I tried to make the problems fit best what we had already talked about, and we hadn't talked about all of the AM topics, so I picked that problem that was AM related, but really what I want you to be familiar with for today is double sideband, and there just wasn't a specific double sideband problem. But this block diagram here is something that is the same as that problem that I referenced, right? Mm-hmm. Except it was for demodulating AM using a coherent demodulator.
Teaching next door, we're out of markers. Can I borrow one?
Yeah, I don't use them. You owe whoever uses them in this class, and I don't know who that is.
So you're not the one who stole all the markers?
No, definitely not. So the elements of this, and this is about as simple as a receiver as you can come across in terms of the high-level block diagram, the low-pass filter and the multiplier. So then the question that was rumbling up here when I came in was non-coherent versus coherent. Why is this coherent? And this was a question I was just getting in my office, too. A coherent demodulator means that the local reference, and this is the local reference. Let's see, get this set right. The frequency and the phase of this reference is perfectly tracking the frequency and the phase of the input reference carrier. Not the message itself, but just the carrier. So here you can see what's perfectly aligning is that and that are the same. If this guy happened to have 2 pi fc t plus theta of t, then if it was perfectly coherent, this one would have to have 2 pi fc t plus theta of t, so that it can perfectly track it. If you put a phase lock loop or some other tracking mechanism in, generally what goes on with a local reference, what the phase lock loop will do, it will produce generally this circumflex. It's kind of a sophisticated name. It's easier to call it a hat, but that's the mathematical term for it. That would be an estimate. So you would have some means to estimate the phase of the incoming signal. So theta hat of t would be approximately theta of t. But that would still be a coherent receiver if that is keeping the error between those two small. And that would be the job of a carrier tracking subsystem in a receiver. RT Logic has those in all of their boxes pretty much. And Emergent, where I work, also, I was there today. They do that. Anybody that needs coherent receivers does that. And the space program has been using coherent receivers for decades because of the added efficiency. And we're not really talking about power efficiency in here so much, but it gives better link performance. You don't have to transmit as much power, like on a deep space mission like the Mars rover. Those links might be coherent links, or the planetary explorers that NASA has had, the ones that go way out there, they will do a coherent receiver scheme. So then what's the opposite of that is non-coherent. And non-coherent just says that we don't care, the demodulation scheme can get by without knowledge of the phase. And we'll have an opportunity to look at something a little bit later that can do that, but a simple example that I think you're probably familiar with is frequency shift keying. If you've ever dialed a phone into a fax machine, has everybody done that at least once? Yeah. Hear that warbling kind of a sound? Frequency shift keying, just the digital modulation is just put on where you shift to a high tone in a low tone with the binary digits you want to send, so you shift high or low. Bluetooth actually uses a form of FSK. It's called Gaussian FSK, but it's still an FSK kind of a scheme, frequency shift keying. It's been used for a very, very long time, but it's more sophisticated, in today's world, but the old-fashioned one was just 2 tones. And that doesn't have to be coherent. It can be coherent, but you can receive it non-coherently. And that has the advantage that you don't have to have the extra processing at the receiver to have a tracking carrier, which means it's good for environments where it's too difficult to track the carrier phase. On a SATCOM link, it's fairly easy to track the carrier phase unless there's pretty wild dynamics going on, like a highly elliptical orbit, so when it passes by, it's sort of zooming around. You've seen how satellite orbits can be circular or highly elliptical, so there can be a high rate of change at the ends of the ellipse. And if that happens to be where the Earth is right in here, when it flies by, it's going to have the phase is going to be changing a lot faster, and then it's harder for the tracking loop to track it.
So, question on the homework problem then.
Okay.
What difference would you see if it was just DSB instead of AM?
On that problem?
Yeah.
Let's see if I have that solution in here. This is set number 3, right?
Yes.
That's the assignment, so that's not the right one. I wanted the solutions to it. I don't see it. I was going to put it on here, but I didn't do that. I can probably pull it off the website, though, if that will cooperate. My machine was clean, started 2 days ago or yesterday, whenever it was, when the Microsoft patches came out. I guess that was on Tuesday. And now my browser probably won't start up. We're waiting. Are there any other questions pending now in the queue?
Does DSB is that like a larger set that includes AM demodulation? It seems like you're using the same process. You're multiplying by a cosine and you're filtering out the higher frequency stuff, and you still have the upper and the lower side bands in AM modulation. So does DSB
Go up a little bit.
Is AM one kind of DSB?
It's probably
DSB?
Yeah.
Keep going.
I should just do that, since I put that in there on purpose to make it easier to find stuff. DSB is double sideband, so that's what we've been talking about.
Right. Does AM
is double sideband plus carrier,
Okay.
so it's like an augmentation.
Double sign plus plus the amplitude.
plus
Yeah, the double sideband, and I can't draw on this, so I can't.
Oh, the amplitude is the carrier.
See if I can make that work. AM is just that for the message, right? It would just be a message with a gain scale factor. AM adds this constant in, and we're going to spend time on that starting as soon as I'm done answering these questions.
Sorry, can you repeat that?
So DSB is.
That didn't
Double sideband is contained within AM
Yes.
Okay.
because it adds this bias term of 1 times the carrier, so it sends pure carrier. Or in the business of stuff I've been working on over the past year for SATCOM, it's called residual carrier. So you add in some pure carrier along with the AM.
So if you just had dual sideband, you wouldn't have the +1
Correct.
in your.
And that's what I meant by this problem being applicable. Is the closest one to double sideband, and because of that, the fact that that constant is in here, when you get through the coherent demodulation process, you now get all of that back out again. And if you have a perfectly coherent carrier, what is that term going to be?
0.
It's 0, right?
So this, even though the input, the modulation frequency or the carrier frequency, cosine of 2 pi fc t, is not the same as.
Let me do something here since this is getting a little bit awkward. I'm going to move this over to my note so I can write on this. If I can get the right folder. Why can't I find the right folder at this moment? Actually, that doesn't work. Let me just poke this in here directly. Now it should be in here.
Yeah, so I guess my question was, does the phase error there, it's negligible because it corresponds to the coherent?
Well, I'm going to tell you, you're not looking at quite right, but I'll get there.
Okay.
I've got to go to 3 again. See, this AM signal doesn't have, there's no theta of t in here.
Right.
So if theta of t was here, and suppose this was theta hat of t,
those would be coherent.
Then what would have happened is there would have been a plus theta of t in here, and the reference would have had the hat in it, right?
Yeah.
Multiplied. And then what would have happened down in here, this would have been theta of t minus theta hat of t. And I'd say if it was perfectly tracking and coherent, those two are equal, right? So that's approximately equal to 0. So, does that make sense? Is everybody okay with that?
Yeah, but since there isn't actually a theta t in the input
Right.
AM modulated signal, then can you
Say,
still make that assumption here?
then I would just say theta of t is equal to approximately 0, because it's following what's coming in from the transmitter.
And that's because it says we're using
Coherent.
modulation.
Okay.
Exactly.
Okay.
Exactly. That's the key.
So this is kind of like, it shows a little bit of incoherence, but we're using coherent of non-coherent.
Yeah, we're approximately coherent
Okay.
to within a few degrees. Generally, it's measured in static phase, which would be due to a fixed offset, say due to Doppler, and then there'd be a slope due to a Doppler offset, and then there'd be a random behavior like noise. So it would be.
So it pretty much goes through the same process as it would with dual sideband, except for that last step.
Mm-hmm. And then you're left with this. Your message has now got a bias on it, so it's offset.
Right.
Just like in the envelope detector that we were looking at, and we're going to look at again here shortly.
Okay, so does perfectly on track mean that theta t minus theta hat is equal to 1? Or perfectly not?
0.
Oh,
What the model could be is that it's just rolling. It's just, it's like the two waveforms are just sliding past each other like that. Or they could be sliding very rapidly past. That would be a frequency error if phase is linearly changing. Again, that's going to become more apparent later, but phase and frequency are derivatives or integrals of each other. But a fixed phase is standing still. If perfect 0 phase is where my thumbs are overlapped and it's like that, that could be bad. If it was 180 degrees, that inverts the signal, but if it's 90 degrees, then remember cosine of that would be 0. So the signals, remember from the sound demo, it nulled it out. But generally it's sliding by. And then there's maybe a random term on there like noise, a random effect where it's just sort of moving around in random, and it's not too good that way either. For this class, we don't want to talk too much about random behaviors, but comm theory people have to deal with that all the time. But you will be dealing with it in your projects, though.
What does that project do?
And I want to talk about that at the end of the period, just before the quiz, if we can get there. That's due on the Friday before spring break. It's the 22nd. That's my plan right now. I think you can do it.
One report per team, right?
Yes, exactly. So form your alliances. Okay, so we're going to go back over to amplitude modulation, which is kind of where we left off. In amplitude modulation, like we've been saying, adds in the bias term. So it adds in, this term is now added on to the message that we had before. So that way we've got a pure carrier term present. And if you look at the waveform that you get with the addition of the bias, it creates this separation between the envelopes. And for that really to make sense, you have to go back and look in the time domain at what was happening for double sideband. And for double sideband in the time domain, we have the waveform here on the right. So this is what the real waveform is doing from the picture over here. But because the carrier comes along and multiplies it, it can switch signs because the carrier is a sinusoid going between positive and negative 1. So it creates this envelope, and the envelope is just the outline of what the wave shape is taking on because of the high frequency carrier inside of there. But when you go to the amplitude, pure amplitude, or AM, when you add in the pure carrier, and this is, I need to have, my eraser's not working right now either. What'll happen when, I think I have a Mathematica slider demo of this, but I just don't remember exactly where I've got it, so I could bring that up, but rather than mess around with that too much. If I add in the pure carrier, though, this thing comes down, and I'll just draw it more as a sine wave, and so you can think of that as pulling up, and this is pulling down. So now we've got, and I didn't draw it symmetrically, but now it's like the teeth of a comb, or it's like my fingers were together with the two waveforms, envelopes overlapping, and now I pull them apart. So now they're not touching anymore.
Because of the amplitude modulation?
Yeah, because of that bias added in there,
right,
of pure carrier that allows it to separate like that. In the frequency domain, it's not really that much different, and I think that's probably what maybe you were being perplexed about, Rob, because in the frequency domain, let me just get rid of some of that clutter. In the frequency domain, this is the double sideband spectrum. If I add in pure carrier, all I'm doing is I'm going to increase a pure spike sitting there at the carrier frequency. A much different view of things than what the time domain does. But that's what the pure carrier is doing. So it's just allowing the envelope to now be separated at the expense of adding in all of that carrier power. But this was the discovery back in the first part of the previous century, the 1900s, that if you did this, then you have this separation like I was talking about last time, so that you can come along with the envelope detector and slice half of that, the top half, and keep it, and then send it through the low-pass filter, and that allows you to demodulate the message with no coherent reference whatsoever. So it becomes a non-coherent receiver using the envelope detector. So with regards to our discussion about coherent and non-coherent, this is even simpler than having a local reference that's not of the right frequency. It just says I don't even need to have a reference at all. I can just envelope detect it. But it's still called a non-coherent receiver.
This is?
Yes.
Okay.
And AM is called a non-coherent technique because you can receive it non-coherently. But the homework problem was to say you can also do it with a coherent receiver, but no one would typically want to do that. I think I mentioned to you that what service uses AM besides talk radio? Aircraft uses AM to talk to the tower. When they're approaching the tower, they use AM modulation. And if you get a police scanner that tunes the aircraft band, you can listen in as the aircraft talk to the tower on final approach. I mean, I've got one in my office. I haven't listened to it lately, but when I was much younger, I was fascinated with listening to police and fire and aircraft. Police and fire you can't listen to so readily anymore because they use digital and they scramble it because it became basically something that the criminals could use to try to counter the police who were about ready to arrive on the scene. They knew what was happening. Or I think you can still listen to fire, but people would still listen if they listen to it. They have people that like to go look at fires, right, or tragedies, and then that kind of makes the public safety people upset because too many people are showing up on the scene. Or in its day, the illegal thing, which happened, was the early cordless phones used bands that the scanners could tune into. So I can remember being in an apartment complex and turn on your scanner and you can hear somebody in a nearby apartment talking on their cordless phone, and you weren't supposed to do that, but if the scanner stopped there because it was scanning the frequencies, did any of you ever do that?
Mr. Incredible did.
Okay. See, in my era, people would do that stuff all the time, but as time moves on, you guys have been fascinated with other aspects of technology, and what I just mentioned was kind of uninteresting, but that was stuff that was, I guess, maybe more from my era. Makes me feel old, but old and happy to say that I had fun doing it. Okay, so in order to make AM work, it has this modulation index A, which is used to represent effectively how close you are to having those two, the envelope, the positive half of the envelope and the negative half, from just touching. So A is defined in such a way that when A is equal to 1, it just touches. So if A was equal to 1 over here, if A happened to be equal 1, then you can see from this equation here we'd have 0, right? And on this side over here the same thing would happen. So it would just be touching, and that's called 100% modulation, where it's just touching. If you were to increase A greater than 1, what's going to happen? Because there's no law against making A greater than 1, you're just not doing, strictly speaking, AM anymore.
It goes back to double sideband.
It starts to go back to double sideband. So this starts to, cross in here, and this one starts to cross above. It's starting to head in that direction again as A were to get bigger than 1.
Cool.
But in an AM radio, if the transmitter is going over 100%, you get a very distorted reception because basically you're getting the signal clipped. Because if the envelope detector works by clipping off the positive half, and if the waveform is passing negative, that gets clipped off. Actually what you get is this comes down and then the other piece comes up. Mm-hmm. So you'd get something like that.
Would you get extra noise too?
It just sounds really crappy, It's very distorted sounding. And those of you in the lab will be building a receiver to do that, and then you'll be trying to listen to it, and you'll experience that it doesn't sound too good.
Is that lab 3, 4?
It's in lab 3. It should be. So what are some of the definitions involved here? The normalization is such that the magnitude of the minimum is divided by A, and that's how you define the modulation index. And the normalized message is just normalizing the message so that on the negative excursion it's equal to 1. So the way the negative message is set up, no matter how it's defined, if it was something like that, the negative value that the message takes on hangs at -1 as its smallest value. That way, when you turn A up to 1, it'll just be touching. This little exercise right in here is really kind of old-fashioned, but it pertains to what you would see on the oscilloscope if you were trying to make a measurement of the modulation index from the waveform. So I kind of have this still in my notes, and it's helpful in the lab, or it can be helpful in the lab. Because it basically says from this picture right here, and just because it's old-fashioned doesn't mean I won't put this on a quiz or an exam. I mean, it would be useful. It could be very useful on a quiz or an exam. It just says you take the peak to peak minus the valley to valley. So peak to peak is measuring this guy right here. That's D1, and then D2 is coming in and making that measurement. When you form that ratio, that's the modulation index. It does have one assumption, though. It assumes that the message is symmetrical about 0. So it doesn't work exactly if the waveform was not symmetrical about 0 in its amplitude swings. And there's the proof of it. You can just look at the proof. We talked about this last time. I did the picture here on the SPICE simulation of adding the filters in.
So how do you choose the R and C values in order to get the correct
Filter.
You want to choose the RC time constant to be, let's see, I think I had it written down in here.
That picture. Yeah, go up. Right there. That's very good.
Yeah, it's right here.
Okay. Oh. Is W the highest frequency?
Of the message, yeah.
Okay.
But it's approximate because a first order low pass filter doesn't really roll off that fast. And if your carrier frequency is rather close, you end up in a dilemma where too high of an RC time constant is going to take some of the message out, and it will leave, but it will get the carrier suppressed. But not enough RC time constant means that you still have quite a bit of carrier left in there. So you can see in this example here, I've got still some of that buzzing is what I'd call it. I call this buzzing on the waveform. If the carrier frequency is high relative to the message, though, then it's not really a problem because it's very easy to have that low-pass filter roll off at that carrier frequency to get rid of all that buzzing and not take any of the message out with it. It's harder in the lab, though, because you don't necessarily have the carrier frequency up that high. So when the two are close to each other, to the message and the carrier frequency, then it's harder. You just have to accept some of this buzzing action. But if you send it into an audio amplifier or headphones, it will reject it, and your ears don't hear it anyway because it's above what you can hear with your ears. But you don't want too much of that coming through because that could overload your audio amplifier if it could respond at that higher frequency. Or create intermodulation and all those other bad things we talked about if it overloads it. The spectrum is like I was showing in the picture earlier. It's the double sideband spectrum overlaid with two spikes, positive and negative frequencies for the carrier. So then in the next topic, and this will maybe be the topic of next week's quiz, or we might not have a quiz next week in preparation for the exam the following week, but I might have a mock quiz just to give another example problem before the exam. Is that shocking to anybody? We had that discussion on Tuesday about the exam.
Right.
Let's pause for a second to refresh memories since
Yeah, it's
a couple people weren't here.
We voted.
It's the Tuesday.
I'm shooting for this day right here, especially for senior design, so there's a little bit of cushion because you guys in senior design are going to be preparing your slide sets, and the all and out panic will be here. And if you're up 2 nights in a row really, really late, I don't know, you know what it's like, but that's just a little bit more stress. So I'm heading for the 12th, either that or the 7th. Can I just lock this and make this a done deal?
Log it in.
Like to walk
Nobody's
around.
questioning, right? We're going to go for it, okay? I'm happy with it.
I am too. Hopefully I'll be happy on
Okay, so one of the things about AM is the fact that a lot of power goes into this pure carrier. And in order to work problems in that domain, we have to do some analysis. We have to know what all the power is transmitted in the AM signal. So the way we get at that is using the time average operator. So we take the time average of xc squared, and that by definition of the time average operator is the power. So this is going to be P total is that. And this gives also a little opportunity to work and use some common sense from spectral analysis and the time averaging operation. So when you plug into that what the AM waveform is, and then do some trig identities. So the first thing I did was just I squared that out using the trig identity, and I pulled the 1/2 out over here, and then squared that out into its 3 terms over here. So now I've got all the cards on the table, so to speak, mathematically speaking, and could just go ahead and blast away with the math. But how many terms would I have? I'd have 6 terms, right?
Yeah, I think so.
Do you want 6 terms, or would you rather have 3 terms? So the idea is to kind of back up and say, can we dispense with 3 terms? And so from the time average operator notation, what, in the modulation theorem, what does this double frequency carrier do when it operates on all 3 of these guys here? For the modulation theorem times a baseband signal, which is what the message is, or the message squared, it'll shift them. So instead of being centered at baseband, they now shift up, right? High and low. As long as the message is slowly varying, this is the notation of the book, which means as long as the bandwidth of the message is narrow compared to the carrier frequency, when we're looking at what's going on in the frequency domain, suppose it's like -2 FC, and it shifts up to +2 FC. The big deal is that this is 0. And the time average operator, the way you can think of it as, is it's looking for things at DC, because that's what the time average represents, action at DC. As long as the message bandwidth is narrow relative to the carrier or twice the carrier, there's no spectrum that's lapping into the DC area.
Okay.
Does everybody agree with that?
Yeah.
So if no spectrum laps into the DC area, what can the time average recover?
Only the DC portion.
And if there is none, so it's 0. Does that make sense?
Yeah.
That's why Fourier analysis can be so powerful. You don't have to sit there and think in the time domain. You can just reason it through and say, if the spectrum doesn't lap around DC, the time average can't possibly be anything but 0. So the impact of this term in this calculation can be eliminated because it doesn't bring anything to the final solution. So now we're just left with the 3 terms, and at this point the book makes the assumption that the message signal is got a DC or a 0 average value. So it assumes that the message average value is 0. And that's a pretty reasonable assumption for most digital schemes, and certainly for analog communications, because generally the analog message is sent through a coupling capacitor or some AC coupling means in the electronics. So if that's true, the time average of this term is 0. So now we're left with 2 terms. And that's about as far as you can take it until you have a specialized form for the message. So that allows you to break it out into the pure carrier. No surprise there that the amplitude of the carrier squared over 2 is the power in the carrier, right? And then we have the little a squared AC squared over 2 times the time average of the normalized message signal squared. And that's the power in the sidebands.
Okay.
So from an information transmission standpoint, the sidebands is what we care about. That's where our message lies. the carrier power has been added in here to make the receiver, a non-coherent receiver, work. So the efficiency of AM is defined as the power in the sidebands over the total power. And that's this formula right here. It's just simply been, there's cancellations that have been included in there. The AC squareds have gone away because they're in both terms, and the 2's have gone away. And then you can massage it a little bit and get it into that second form if you want to. I really like this first form better because the modulation index is exposed, and that way you can see the impact of that in the analysis. So this first example takes a single sinusoidal message. So the message is just, that's m sub n of t. And remember, m sub n of t is m of t divided by the magnitude of the minimum value of m of t. What's the minimum value of a unit amplitude cosine? It's -1.
Yeah.
So you're normalizing by absolute value of -1, which is 1. So you don't have to do anything with that. So plug that in. Set the modulation index equal to 0.8. And this problem starts off by saying the transmitter is broadcasting 1,000 watts. For AM radio, this would be really low power, relatively speaking. Most of them are in the kilowatts of power. But at any rate, that's the total power. So P total is 1,000. And that's the power in the carrier, and then the power in the sidebands. And because our message signal is this cosine, it has a power of 1/2 in its normalized form. So that's why there's a 1/4 thrown up in here, because that's the 1/2 times the 1/2 that comes from right up in there. So this is just a squared. Put those numbers together and you get the 33 over 50 times AC squared.
So what happens to the pi over 3? The shift, the phase? Do we care about that?
No?
Oh, because it's time average?
Yeah, time average. We're just looking at powers.
Okay.
In a problem, though, that would be clutter thrown in your problem to kind of see, do I need this for anything or not? Right?
Well, that's what I mean.
Isn't that true of everything you've ever done, though? Sometimes you're given more information, and that's an important learning process, to learn what you need to pay attention to and what doesn't matter. So you work those numbers around to solve for AC, and once you have AC, then you can go back and solve for the power in the carrier, and then solve for the power in the sidebands. This seems like the problem is being worked backwards, but if you were the Federal Communications Commission and they were telling you could broadcast 1,000 watts with your low-power AM radio station, this is how they'd be looking at it, and you'd be having to think of it this way. So the efficiency is only 24%, which I think is pretty low down, but that's the way AM is for the single sinusoid. I put together the spectral plot here, just the full magnitude and phase plot. It's not that relevant to most of our discussions. I'm not sure why I put it in here, probably because the book had it. I'm not sure. And I didn't draw it to scale either. If it was drawn to scale, it would be, the sidebands would be a lot lower relative to the carrier power. I do have another example later I did in MATLAB which shows everything to scale. And it looks tiny. It looks like the information is dwarfed next to the pure carrier. It's kind of like if you were getting beat over the head with the carrier, you'd say, where's the message? I can't tell because the carrier is so powerful, but in the demodulator, the carrier is just that DC bias that comes out of the envelope detector, so it's not music or anything. You'd remove that with AC coupling and the electronics. There are certain types of signals that can get higher efficiency, like the pulse train, for example. And the pulse train can do that because you can change the duty cycle. Here, if you have the pulse train as shown in this picture, you can, once you have the negative value of the pulse train biased down at -1, you can change the duty factor and you can get much higher values of efficiency if you go through the math on this problem. I'm going to let you guys study that one on your own. I've got it worked for both types of pulse trains, either the high duty cycle or the low duty cycle. But you can get efficiencies much higher. But suppose you came to your senses and said that doesn't look like a real information signal except for maybe radar or something. If you went with a 50% duty cycle square wave, which is just, you know, a modified sinusoid, as if it's clipped, you can get the efficiency up to 50% maximum, which is still not that awfully good. That would be with 100% modulation.
So with like a 70% duty cycle, is it linear? So like 70% duty cycle would be 70, or not? But not 70.
It's, well, you can see for the pulse train, it's what this equation has in it. This is for 33% duty cycle.
Oh, okay.
But yeah, you can approach 100% efficiency for this guy. How? You look at that equation, you can see if at the duty factor, which is right, let's see, the duty factor shows up in here indirectly. I guess I don't have it worked out though. The duty factor is right here though, is the 1/3. And when combined with the 2/3, it gave you the 1/2. I don't have it worked out, but I know that it approaches 100%. But then you're sending like this zero duty factor waveform, which doesn't represent anything practical unless it was, like I said, a radar kind of a signal. And radar would be the only example that I can think of where that would make sense. Send a very short pulse like that. When you have multiple sinusoids, you start to see what goes on in a real receiver, where you don't have just a single sinusoid that you can say, this is the minimum, I can normalize it like this, I can figure it out. When you have multiple sinusoids, to get the normalized message, you have to find out what the minimum value is of m of t. So you can lower bound it by saying it's just the negative of the sum of the peak values. And I have the little comment in here, why. Why would that lower bound apply? Think of a bunch of sinusoids. If they were phased and frequency set up properly, what's the worst case scenario in terms of positive to negative swings? Where they all add up, right? But that doesn't necessarily happen with a given setup. And with a random kind of a waveform, it wouldn't happen at all. But here, there were 3 frequencies, and the only way to really get this to work out is to actually simulate it in MATLAB. So I plotted it out in MATLAB and found the minimum value there to be 7.246. And it's something like 9.7 or 9.5 or something if you add the amplitudes up. So it's not quite the worst case. So you'd have to divide everything by that value to get the normalized message. And then if you go through the rest of the analysis, this is just plots I made to see that the envelope does correspond correctly. In particular, this plot right here, where I set A equal to 1, notice that the envelope is just touching, which is what we'd expect it to do. But most of the time, it's a long ways away from that. Go through the efficiency in this case, again, you come back at about 24%. There's a couple of problems like this in the homework in the book. Obviously, this doesn't make for a very practical quiz problem or exam problem because you're not going to run MATLAB. So I would have to provide some extra information, but you need to be aware of how the normalized message enters into the equations, and that you have to first find out what that normalization factor is. So in here, this is the calculation for the power of the normalized message when you have multiple sinusoids. So I get the power of the normalized sinusoids through their amplitude squared over 2, but then I come along and square by the normalizing factor, or normalize by that minimum value squared. And then that enters the previous calculations that we used. And this is, when I say maximum efficiency, this is when A is equal to 1. That's why you don't see A in the equation down there, because I assumed A was equal, modulation index was equal to 1. And here's where I plotted it in MATLAB. So all the sidebands sitting down there look kind of like accidents sitting next to the carrier. It's just because that's the way AM works out. This is 50% modulation index. So I could double the height of those guys if I took A up to 1, but it's still only going to bring, and the values are going to come up to being in here.
So you said you want those sidebands, right? Present?
Yeah, because that's where the information is.
Right. Okay.
It's just that you have to send all that power in the carrier. And you have to think, why are we doing this again? It's so the non-coherent, simple non-coherent receiver can work, the envelope detector. Okay, I want to spend a couple of minutes introducing single sideband and then talk a little bit about the project, but save the rest of the math on single sideband until next Tuesday. This topic is motivated by the fact that when we started with double sideband on Tuesday, we noticed that there was a symmetrical upper and lower sideband sitting in the signal. In other words, if I concentrate just on a single-sided spectrum plot here, if my message goes out to W, then double sideband modulation has a total width of 2W. And intuition says both of those sidebands contain the same information, so could I get by with sending only one of them? And that's what the plan is here. So lower single sideband will remove the upper sideband, and upper single sideband will remove the lower single sideband. So now you're only consuming half the bandwidth. And what you can do with single sideband is you can actually, I just wanted to make that look different. This would be like message 1, and you could pack message number 2 right next to it. So you could fill the channel with twice as much information, twice as many messages per hertz of bandwidth with the single sideband.
That'd be a different signal, though.
Yeah, it'd be another user.
It wouldn't look anything like necessarily.
Yeah, I tried to make it look different by squiggling it, but this is what the telephone company did for decades and decades on wired lines. This is how the switching center took the information from the home and relayed it across the country by microwave tower before we had fiber optic, digital fiber optic means. Everything was done with a hierarchy, and everything was done in this fashion where they used single sideband because they could double the capacity that way. It's still used for shortwave. And it's used by amateur radio people, and it's got certain specialized applications. And the technique, though, the idea of being able to conserve bandwidth is valuable unto itself, and getting introduced to the Hilbert transform is also valuable unto itself. So what we have to do to understand how double sideband can be formed is learn about the Hilbert transform, and we'll jump back into chapter 2 just for a bit to learn about that. And that's also the basis for the project, just so that you have something that's different to build up. So I'm just going to take a quick look at the project. So what the project does, I'm just going to look at the block diagrams. The project has you build up this block diagram in a MATLAB simulation. So you have to build up a modulator, and then you have to build up a coherent demodulator. You don't have an actual antenna in your system, so whatever you use to modulate, you can use to demodulate. You have an easy, what I call the magic genie signal, will be available within the MATLAB simulation. So but your modulator will be a module of code that can take the audio files. Remember the speech files we played with last time? That will be these guys here that you'll have to experiment with as inputs. You will have a variable to toggle whether it's upper sideband or lower sideband, and then you'll have another variable to set the carrier frequency. And then you have you sum the signals together as if you're superimposing multiple types of messages. Then you have a bandpass filter at the receiver front end to limit what can get into the receiver. And I'll explain that more as you get into this, because it's kind of like protecting the receiver from the processing blocks in terms of leakage signals and so on, interference. But the goal will be to demodulate either 1, 2, or 3 and minimize the interference from the other signals. So you'll be putting the 3 signals up on carriers that are somewhere between 16 and 32 kilohertz. So the simulation runs efficiently enough in MATLAB. It's not at a really high frequency, but it's up there a little ways. And then you'll be playing with how close you can space them and be measuring how much interference and junk that you get through. Like the hardest channel to receive is going to be this guy right here, because it has 2 neighbors, whereas the signals on the end only have 1 neighbor.
Is the spectrum that you can hear from is from around, it's like 0 to 15,
0 to 20K?
Well,
these messages here are all 0 to 4 kilohertz. Because they're sampled at 8 kilosamples per second, so the folding frequency or the usable bandwidth from sampling theory is 0 to fs over 2.
And should we implement the filter using one of the digital filters in MATLAB? Like
Yeah. Yep, that's what you have at your disposal. No, I'm not limiting, but I don't want you to be crazy about it. Because if you build a really high order filter, it will work beautifully. But would you implement it that way? It would be expensive in terms of CPU cycles. Now this is going to be done in DSP. So we have to, and I give you certain pieces of the code are pre-built. But the modulator itself came from an article that I found on the internet. It's called Weaver's modulator, and then it's a DSP version of Weaver's modulator. So first, it's the Weaver's modulator in the analog form, which looks like this. This is a single sideband modulator. We're going to go through the math next week, and we'll see the math, and we'll see the Hilbert transform does its thing. This does the implementation without the Hilbert transform in the direct form. This is more or less an indirect way, but this is a way that's more implementable in hardware or in a software simulation. So this is what you're implementing in code, but you're actually going to do it, and here's some discussion on the filter types you can design in MATLAB. I assumed when I wrote this a few years back, I assumed that people didn't necessarily remember much from 3205 or 2610, difference equations and so on. But this is what the actual modulator will look like that you'll implement. You bring the signals in, you have a filter, and then you upsample by a factor of 12. And upsampling is something that you learn about in modern DSP, but not in 3205. So there's a little discussion on it in here. You're just going to up the sampling rate by a factor of 12. So it will go from 8 to 96 kilosamples per second. And the upsampler has to have a low-pass filter inside of it, so you'll implement that as well. And then you have your transmitted signal that comes out over here, and then your demodulator pretty much has to undo this with a means of selecting it off the proper carrier frequency, and then it has to decimate the signal back down by a factor of 12. So it decimates it from the 96 rate, decimates by a factor of 12, and takes it back down to the 8K, and then you'll be able to listen to it using MATLAB's sound function.
Why again do we need to up it by 12?
Because right now, if you only operate with 8 kilosamples per second, there's no means of placing it on carrier frequencies that are that high.
Right.
Whereas if I operate at 96, my folding frequency is up here at 48.
That's FSO2.
Yeah. Does that make sense?
Yeah.
So we need to up the sampling rate so we can move it up in frequency. And this is exactly what DSP implementations do all the time. They have to play around with upsampling and downsampling for comms applications.
Okay. But, and you can't leave it at the high sampling rate because it won't play back.
In MATLAB, you can't play back at, well, the codec in MATLAB in your computer might handle 96K, but it's throwing out lots of bits, lots of samples per second that are unnecessary for a message that only has a 4 kilohertz bandwidth, so you downsample it and then send it out.
Okay.
This is called multi-rate signal processing, and it's done all the time in all the audio devices like your iPod or anything communications and audio signal processing oriented does multi-rate processing these days. It's pretty cool stuff. It's the modern day version of analog electronics in my mind. It's how you manipulate things by doing it all in DSP. Well, we got to get started with the quiz at this point. Any last minute questions?